Hey everyone, and welcome to today's explainer on the totally fascinating properties of 3D solids. I'm thrilled to be your guide for this 8th grade geometry deep dive. You know those boxes arriving on your porch? Or the soup cans sitting in your pantry? Well, today we are going to break them down mathematically. By the end of this, I promise you're going to see the 3D world around you in an entirely new way. Seriously, you might never look at a soup can the same way again. Here is a quick look at our roadmap for today. We're going to kick things off with polyhedra versus curved solids, then jump into classifying prisms and pyramids. After that, we'll do pause check number 1, move on to folding shapes using nets, hit pause check number 2, and finally wrap it all up with a recap and our transfer question.
All right, let's dive right into section 1, polyhedra versus curved solids.
So we are starting our journey by drawing a hard line between two totally distinct families of 3D shapes. Over on the left side, we have polyhedra. A polyhedron is a solid figure where absolutely every single surface is a flat face with straight edges. Think of your classic rectangular solid or a cube. They are built entirely out of flat geometric planes. But then, on the right side, we have our curved solids. These guys are completely smooth and lack those sharp, flat edges entirely. Think of a basketball, which is a sphere, or a can of soda, which is a cylinder, or even a party hat, which is a cone. These curved solids play by a completely different set of geometric rules than our flat-faced polyhedra.
Moving right along to section 2, classifying prisms and pyramids.
Okay, so just calling something a polyhedron is kind of like calling a Ferrari just a vehicle. We need to be way more specific. The absolute most crucial thing here is that you don't just look at the sides. You have to look at the base to figure out what the shape actually is. The base is the geometric anchor. It literally dictates the mathematical identity of the entire figure. And here's a quick tip. In math, the base isn't always just the side the object happens to be sitting on. It's a very specific defining face of the polygon.
Whether you're dealing with a prism that stretches between two identical bases or a pyramid that tapers up to a single point, that base polygon is what runs the show. For example, a rectangular prism, like a standard cardboard shipping box, has two parallel rectangular bases. A triangular prism, it has two parallel triangular bases. Pyramids, on the flip side, only have one base. So a rectangular pyramid has one rectangular base, with triangular sides that shoot upward to meet at a single vertex at the top. A triangular pyramid has a triangular base, and again, sides meeting at a top vertex. Basically, the name of the base gives the shape its first name, and whether it has two parallel bases or meets at a point, that gives it its last name.
Time for section 3, pause check number 1.
Let's test your immediate recall here, because active recall is hands down the best way to lock these definitions into your brain. Think really carefully about the geometry of a cylinder's sides and bases. Picture a can of paint. Based on what we just talked about, does it fit the strict definition of a polyhedron, or is it a curved solid? Well, if you pictured those perfectly round circular bases, you hit the nail right on the head. A cylinder is absolutely a curved solid. Sure, it does have two parallel bases, kind of like a prism, but those bases are circles, not polygons. And the side connecting them? It's just a smooth, continuous curve. Because it completely lacks those distinct flat polygonal faces and straight edges, there's just no way it can join the polyhedron club.
All right, let's jump into section 4, folding shapes using nets.
This is where things get incredibly cool. We're bridging the gap between flat, 2D drawings and the 3D space we actually live in. Imagine carefully taking a cardboard box, cutting it along its edges, and unfolding it completely flat onto your kitchen table. What you're looking at is called a net. A net is essentially a 2D map of a 3D shape. In 8th grade geometry, you're going to represent 3D figures using these nets all the time. And it's not just a fun origami exercise. It is exactly how we visually break down a complex solid so we can calculate things like surface area later on. Just try to picture that flat cardboard unfolding in your mind, hinging upward perfectly at the edges to trap the empty space inside. When you look at the net of a rectangular solid, you are seeing all 6 of its faces laid out totally flat. You've got your front, back, left, right, top, and bottom. Step 1 is identifying this central rectangle to act as your stable base. Step 2, you mentally fold up those attached side rectangles at perfect 90-degree angles. And step 3, you fold that final top piece over like a lid. By doing this, you can literally see the 3D shape before it's even built. Moving into section 5, pause check number 2. It's time to really test that mental spatial reasoning. And hey, if you need to close your eyes to visualize this one, go for it. That's exactly what real mathematicians do. So mentally hinge those 4 triangles upward from the square base and visualize where their points will end up. what happens when those four triangular faces meet in the air? Did you see it? Because the base is a square and the sides collapse to a single point, our classification rules confirm it is a square pyramid. The square grounds the shape as its base, giving us its first name. The fact that the surrounding net pieces are triangles that fold up to a single vertex, that tells us its last name is pyramid. And finally, section 6, recap and transfer question. Wow, we have covered a ton of ground today, so let's quickly pull it all together. These 3 core takeaways are your absolute building blocks for mastering geometric volume and surface area. First off, always categorize your solid. Is it a flat-faced polyhedron or a smooth curved solid? Second, if it is a polyhedron, find the base to properly name it as a specific prism or pyramid. And third, always remember that any of these 3D shapes can be unfolded seamlessly into a 2D flat net. Now, I'm going to leave you with this really provocative challenge. Think about how adding up the 2D areas of that folded net relates to the actual total surface area of our 3D world. If you wanted to wrap that rectangular prism like a present, and you had its 2D net flattened out right in front of you, showing all those sides, what simple mathematical calculation could you do with those flat rectangles to find the total surface area? Really ponder that connection between the 2D net and the 3D surface area. It's total game changer. Until next time, keep visualizing the geometry around you.